Have you ever fixed a bug in one part of your code just to watch two new, completely random bugs pop up somewhere else? Yeah, it's one of the most maddening things about being a developer. Well, today we're going to talk about the 5 principles that can help you finally stop that cycle. We're diving into the solid principles to see how we can write code that's flexible, maintainable, and, actually works. Okay, first things first, let's just bust a huge myth right out of the gate. We're all taught that object-oriented programming is amazing because it models the real world, right? A dog is a type of mammal, so we use inheritance. But according to Uncle Bob Martin, the guy who really put these principles on the map, that's just marketing talk. The real point of good OO design isn't to model reality, it's all about one thing: managing dependencies. That is the entire game. So, what happens when we don't manage those dependencies well? We end up with code that's just a total pain to work with. We get code that breaks all the time. And that pain actually has a name. In fact, there are 3 key symptoms of a poorly designed system. First, there's rigidity. That's when one tiny change forces you to hunt down and change a whole bunch of other things. Then you've got fragility, which is even worse. That's when you make a change and something breaks in a totally unrelated part of the system. And finally, there's immobility, where a piece of your code is so tangled up that you just can't pull it out to reuse it anywhere else. Sound familiar? I thought so. This is exactly where Solid comes to the rescue. Look, it's not a silver bullet, but it is an incredibly powerful set of guidelines for fighting back against all that rigidity, fragility, and immobility.
Solid is really just an acronym for 5 design principles, and when you use them together, they help us create software that's just better. It's easier for the next person to understand, it's way more flexible when, not if, the requirements change, and it's so much easier to maintain down the road. So, let's break them down one by one.
We're going to start with the first 3 principles: S, O, and SOL. These are really all about how we design our individual classes to be way more robust and focused. First up, we've got S for the single responsibility principle. The definition sounds simple, but it is so powerful. A class should have only one reason to change. Now, this doesn't mean a class can only do one thing. It means that all the things it does should serve a single overarching responsibility. So let's look at a really clear example. On the left, we've got a calculate areas class. It sums up the areas of shapes, and it also outputs the result. That's 2 responsibilities, right? 2 reasons to change. So if your boss suddenly says, hey, I want the output in HTML now, you have to go in and modify the entire class, even the calculation part that works perfectly fine. By applying SRP, we split it. We now have a calculate areas class that only calculates and an output areas class that only outputs. Now you can add JSON or PDF output formats all day long just by changing the output class, and you never have to touch that stable, reliable calculation logic. So here's a great little rule of thumb for you. If you find yourself describing what your class does and you use the word and, like it calculates areas and it formats the output, that's a huge red flag that you're probably violating the single responsibility principle. All right, let's move on to O, the open/closed principle. Now, this one sounds like a bit of a paradox at first. It says our code should be open for extension but closed for modification. What does that even mean? Well, it means we should be able to add new functionality without having to go back and change our existing battle-tested code.
Let's go back to our calculate areas example. Imagine it's hard-coded to only work with rectangle objects. What happens when we need to add a circle? Well, we have to crack open that calculate areas class and modify it. It's not closed for modification. The solution here is to rely on an abstraction. By making our calculate areas class work with a generic shape interface, we can create brand new shapes, circle, triangle, whatever, and as long as they follow the shape contract, our original calculation class never ever has to change. It is now open to new shapes but completely closed to modification.
The L stands for the Liskov substitution principle. I know, it's named after Barbara Liskov and sounds super academic, but the idea is actually pretty simple. It just means that if some piece of your code works with a parent class, you should be able to swap in any of that parent's child classes, and the code should just keep working perfectly without even noticing the change. This leads us to a classic, almost philosophical debate in programming. In math class, a square is a special kind of rectangle. So it's really tempting to model it that way in our code, with class square extends rectangle. But should we? Well, think about it. A rectangle needs a separate length and width. A square only needs one side length. If square inherits from rectangle, it has to do weird things to fake the parent's behavior, and that can lead to some really subtle, hard-to-find bugs. A square does not behave like a rectangle in every context. So the better design is to have both square and rectangle inherit from a more abstract shape. Now they are both valid, truly substitutable shapes. Our code is more logical and way less surprising. All right, we've covered how to design better, more robust classes. Now let's zoom out and look at the last two principles, I and D, which are all about how we manage the connections between those classes.
The I is for the interface segregation principle. The core idea here is simple. Clients shouldn't be forced to depend on methods they don't actually use. Basically, we want to favor lots of small specific interfaces instead of one giant do-everything interface. For example, look at this I-mammal interface. It's got methods for eat and make noise. That works great for a dog. But what if we have a weird mammal that, absorbs nutrients through its skin? It doesn't eat. It would be forced to implement an eat method it doesn't even need. The solution is to segregate or split the interface. We create a tiny I-eat interface and a tiny I-make-noise interface. Now a dog can implement both, but our weird nutrient-absorbing mammal can just pick and choose what it needs. This makes our whole design way more flexible. And finally, we arrive at D, the dependency inversion principle. This is really the culmination of all the other ideas. It says that our high-level business logic shouldn't depend on the low-level, nitty-gritty implementation details. Instead, both the high-level and the low-level parts should depend on abstractions. We literally invert the normal flow of dependency. Let's walk through this journey. In step 1, our cat class has the meow logic baked right into it, super rigid. In step 2, we make it a little better by creating a separate cat noise class. But our cat class is still responsible for creating a new cat noise object itself. It's still tightly coupled to a concrete class. Now step 3, this is where the magic happens. We create a generic mammal class that knows nothing about cats or dogs. All it knows is that it needs something that can fulfill the making noise interface. We then inject that specific noise-making behavior, like cat noise, through the constructor. Now the high-level mammal and the low-level cat noise both depend on the making noise abstraction. They are completely decoupled. That is powerful. So we've gone through all 5 principles, SOLID. What's the big picture here? What does it really mean to think in a solid way? If you remember just one thing from all of this, let it be this. The heart and soul of Solid is about managing your dependencies. And you do that by coupling your code to stable abstractions, like interfaces, not to volatile, concrete details. And you know what? This way of thinking leads directly to a really powerful modern design philosophy, favoring composition over inheritance. Instead of building these rigid family trees of classes, we build flexible objects by composing them from smaller, independent behaviors, just like we did with our mammal and its making noise behavior. It's a fundamental shift in how you approach building things. And that brings us to the end. The solid principles aren't just some abstract rules to memorize for a job interview. They are practical, everyday tools for writing cleaner, more resilient, and frankly, more enjoyable code to work on. So I'll leave you with this thought. The next time you sit down to start a new project or a new feature, how are you going to make your design just a little more solid?